Hey, first of all, I'll begin by thanking the organizers for inviting me to give the talk at this conference. It has been a great learning opportunity. I'll be talking about this work that's close to being completed. We'll put this up on archive soon. The work I'm going to talk about projected ensemble, the idea of projected ensemble in a system with local conserved charges. Locally supported conserved charges. This work was in with a PhD student at IISc Pune and Sthitadhi here. This is the plan of the talk. I'll discuss a bit of background on projected ensemble, Scrooge ensemble, and Porter-Thomas distribution, bit string distribution, and then I'll discuss the specific model that we are looking at and look at bit string probabilities in this particular model, and then use that to discuss the moments of the projected ensemble and compare that with what you expect from the Scrooge ensemble, or then discuss the time dependence of these moments and conclude. So I'm going to take a perspective of ensemble of states as some black box that has some probability of generating certain states, and it generates a sequence of states that someone can make measurements on. And if there is such a sequence of state, the observer essentially sees only the density matrix. Even though these states may be distributed in a non-trivial way in the full Hilbert space, the person who's doing measurements can only see the density matrix corresponding to this sequence of states. To make that clear, if you have a ensemble which generates spin up and spin down, or 0 and 1 state with probability 1/2, then the person who is measuring it sees the density matrix as the identity. If instead x plus, x minus, z plus, and z minus are all, oh sorry, not 1/4, then again the person who does the measurement sees only the density matrix, which is identity. The fact that the distribution of states in the Hilbert space is different is not visible to the observer. If you take the scenario of a ensemble that corresponds to a reduced density matrix, you can think of it in this way. The black box that generates the ensemble has a large collection of identically prepared states, and in those states you make a measurement on projective measurements on a subsystem repeatedly, and whatever comes out as the pure state after making subsystem measurement, that pure state is sent out as the sequence of state that I mentioned earlier. If the state psi a z b is are the states that are generated, then these states occur with the probability that is given by this, and so this probability and the state this defines the ensemble, and the observer essentially notices that this ensemble is described by the reduced density matrix of the A subsystem here. Now, instead of sending the information only about the state psi A, if the ensemble passes the information of what was the measured outcome in the ZB component, then it turns out that more information can be gathered. In particular, we can calculate higher moments of the distribution of these states in the full Hilbert space, and you can get information for more than what you can get from the ensemble. Basically, you can know more than the density matrix of this ensemble. To see that, you could. This is a heuristic way to see that this is true. If the ensemble passes on the information about the state that was found, the pure state that was generated on the A subsystem, together with the bit string that was measured in the B subsystem, I can, by the way, these indices 1, 2, 3 are the indices of, you can think of it as a sequence index. Psi 1 could be, for instance, equal to psi 3. So if you group the data by the second component, basically the bit string that was observed, that essentially gives you a list of states which we know would be identical. So all the states with the bit string 0, 0, 0 would be identical states, and therefore, by collecting this information, I should be able to calculate any expectation value, ideally any expectation value of the state, and therefore, I can get arbitrary the probability distribution of expectation values of any operators in the full Hilbert space. And since I have the probability distribution of the expectation values in these in the states in the full Hilbert space, I can calculate arbitrary moments of them. Just to emphasize what I was mentioning earlier, if I just had access to the density matrix, I can calculate this quantity, the expectation value of some observable in the ensemble. That would be the first moment of the expectation value of the observable in the individual states. If you have the projected ensemble, since I have the information about the probability distribution of the expectation values of observables, I can calculate arbitrary moments of this quantity. Yeah, so that's what I mean. These are not different outcomes; they are identical outcomes, but they appeared at different sequence in the, and they're all identical.
They're all identical.
Identical, yeah. And therefore,
Because how many times?
Yes. So by enumerating this, I can get the distribution of the bit strings, and I can also get expectation values of. Okay. The kth moment can be written as trace of some object rho k, which I'll explain in a moment, times the tensor product of the observable O, trace taken in the tensor product Hilbert space of A, kth tensor product Hilbert space of A. And this object rho k can be thought of as the kth moment of the ensemble, which is this quantity, and I'll call this the kth moment. And if I have this information, I can by using this formula, I can calculate the kth moment of any observable's expectation values. The first moment of this is the density matrix, and that is the only information that you can get if you had access only to the density matrix. Higher moments need that, at least you need the information that is passed on in the projected ensemble. Now I'll discuss the idea of Scrooge ensemble. We'll use this in a moment later on. Okay, so if I have a density matrix for some system, the distribution of states, the Scrooge ensemble prescribes a distribution of states in the Hilbert space, the full Hilbert space, which is defined by this probability distribution. Here, psi is a set of states that is picked uniformly on with the Haar distribution, and the state P of psi is associated with the probability that is the expectation value of rho A with the states picked from the Haar distribution, and for that state, the state that is output is square root of rho times the state psi, the normalized state corresponding to that. Yeah. It's a multi-partite state. So okay, for now, that aspect does not matter. Given a density, I'll come to the first part in a moment. Given a density matrix, I can define the Scrooge ensemble to be this rho-deformed Haar ensemble. It is, if you pick psi from the Haar ensemble, I can associate a state square root of rho times psi after normalization with a probability P of psi, which is this, that defines the Scrooge ensemble. Okay, so this was in anticipation of what comes later. So if I have a time-evolved system, if I construct the density matrix for a small subsystem here, then I have a density matrix, and this was in relation to what I will discuss in a moment. Any bipartition. And now, yeah, I'll come to that. And you can think of the Scrooge ensemble as the maximum entropy ensemble in the full Hilbert space given a particular density matrix. You have to define entropy in the full Hilbert space in a careful manner. For details, you can look at this paper, or we can discuss after the talk. Yeah. Okay, for now, you can sort of ignore this. Let's say I have a system with a density matrix rho, okay? And I can ask, what is the ensemble that must have created that density matrix? Okay. The ensemble that contains the least amount of accessible information. Of course, so let's take the identity as the density matrix. It could have been created by, like I said, equal mixture of spin up and spin down, or it could have been created by an ensemble where every state on the every state is uniformly distributed in the hypersphere. The latter will have least information in some intuitive sense. Yeah, that is the Scrooge ensemble. On a subsystem A, so you can pick some subsystem. Yeah, so this psi is different from this psi. Psi is some state picked uniformly from the Haar ensemble. Yeah, sorry. Yeah.
This psi on the definition of Scrooge ensemble has support only on the Hilbert space of A.
Yes. Yeah. Thanks. Sorry. Unique answer for the ensemble, you mean? Yeah, it defines a unique ensemble. This package defines the ensemble.
No, I think your question is that so if you're just given the density matrix, of course there can be many ensembles which give you the claim is that the maximum entropy ensemble is unique, and that's this.
Yeah. So that the notion of maximum entropy is sort of well defined in this. And this
qubit example, as you said, completely mixed state, I can think as equal mixture of sigma z up and down. Also, I can think as R uniform measure of all states. So this is same different ensemble for the same mixed state.
Yes.
So which one is Scrooge ensemble?
Yeah, in that particular context, the Scrooge ensemble will be the one that is uniformly spread on the
uniform. How is the Scrooge?
And you can think of the generalization of that for arbitrary density matrices. That would be the Scrooge ensemble. The one that the uniformly distributed on the sphere will be the case where density matrix is identity.
Yes.
Yeah. So sort of generalization of that to the case where there is a particular density matrix, that's Scrooge ensemble. No, not von Neumann, because once you give the density matrix, the von Neumann entropy is fixed. Yeah, so this entropy is a notion of entropy in the full Hilbert space, not just something that can be defined on the density. It's something called accessible information. It has to be defined a little carefully. You can look at this reference to get some. Okay, if you have a random unitary and evolve if you evolve some state like this, some direct product state like this with a random unitary, and look at the reduced density matrix, the ensemble generated, the projected ensemble for a subsystem inside this, then the rho A is identity. If U is a generic unitary which is maximally mixing, in that case, the Scrooge ensemble for that context becomes the Haar ensemble, as I mentioned earlier. If U has some global conserved charges, then there are two scenarios. If the measurements that you were doing in the B subsystem were charge revealing, then if it was not charge revealing, then the ensemble generated in A would correspond to the Scrooge ensemble. If the measurements that you do in the B subsystem reveal some information about the conserved charge, then it turns out that the distribution that you get, the ensemble that you get in A is a weighted sum of the Scrooge ensemble if the measurements that you do are charge revealing. Now, we can calculate the moments of the Scrooge ensemble. The moments would be given by the kth tensor product of the projector onto the state times the probability of that state in the Scrooge ensemble. And this can be, with some effort, it can be explicitly computed. In particular, in the basis of the density matrix, in the eigenbasis of the density matrix, these can be computed. It has some permutation symmetry in the indices. So let's say, okay, sorry, it should be rho 2. If n and m are two different eigenstates of the density matrix, the matrix elements rho nm nm is the same as rho matrix elements rho mn nm, etc. And that can be shown to be equal to something like this, where lambda I are the eigenvalues of the density matrix. Okay, so, and yeah. D is the dimension of the A subsystem. Okay, so I'll, lambda I are eigenvalues of rho A. X is some dummy variable. It is related to the, yeah, it is related to the projection of the eigenstates into certain bases. Okay, so I'll come back to this formula later. I will use this to compare the measured projected ensembles moments with this. So I'll use this formula later. So the particular model that we are looking at is the L-bit Hamiltonian. The Hamiltonian, we take terms with up to 3 site interactions, and the coupling constants are picked randomly from some distribution, and the width of the distribution from where the coupling constants are taken exponentially decreases with the distance between the terms with non-trivial support. So if Jijk, for instance, Jijk would be exponential, the typical values of Jijk would exponentially decay with the distance between, the maximum distance between the sites I, J, and K. And the key feature of this is that there are local conserved charges which are just the sigma z I on each of the sites. The system defaces without changing the populations of the up and down states on the different sites. And in this particular case, we'll look at an initial state, which is a direct product state with spins pointing on in random directions on the Bloch sphere, and time evolve the system with this Hamiltonian, and then look at what happens to the projected ensemble, or the moments of the projected ensemble in the long time limit. To compare with the Scrooge ensemble, we will consider the second and third moments of the ensemble and take A to be of size 1 or 2 in the numerical calculations. And I'll also look at what happens when you change the measurement angles, measurement basis in the B subsystem. Okay, so before proceeding to discuss the actual moments of the distribution, it's useful to look at an idea of bit string distribution. So if you have a system that is unitarily evolving in some Hilbert space, the sphere is not necessarily the Bloch sphere, it is in some higher dimension. If the state is evolving under some chaotic unitary, then the quantity of interest here is the probability that a particular bit string is observed, and that will be given by Q of t is equal to square of psi of t in a product with Z. So I can think of a table like this where I have several bit strings and different time steps. The probability of measuring a particular bit string changes with time, and for different bit string there I get different time series like this. If I take a particular bit string and look at the time series of probabilities of measuring that bit string at different times, then if I construct a histogram of this, it is known that for a chaotic unitary, the probability distribution has this form, and this is called the Porter-Thomas distribution. It's an exponential distribution with 1 over the dimension of the space. And in this particular case, we have a charge we don't have a generic unitary, we don't have a chaotic unitary, there are a lot of conserved charges, so you would think that this wouldn't approach the Porter-Thomas distribution, the corresponding quantity in this particular case will not approach the Porter-Thomas distribution, but it turns out that surprisingly it does under these conditions. So if at large, if you evolve the initial state with this L-bit Hamiltonian and make measurements in the x direction, basically look at probabilities of getting various bit strings in the x direction measurement, then the probabilities that you get turns out to be distributed according to Porter-Thomas distribution. This is the log of the probabilities, and this is the probability. And irrespective of which bit string I take in the x direction, they all follow the Porter-Thomas distribution. And the mean values are also identical, and they are indeed identical to 1 over d. Yeah. Now, if you make measurements at an angle other than x, by the way, the x measurement is special in the sense that it is the least charge revealing. The charges in this system, the local charges in this system are the sigma z. If you make x measurement, it reveals nothing about the sigma z charge on each side. Instead, if you make measurements at some angle, those are charge revealing. You get some partial information about the conserved charges if you make measurements at some angle. And in that case, it turns out that we still get Porter-Thomas distribution for the bits, for all bit strings. However, the mean value for the distributions for different bit strings are different. So these are the probabilities of the measurement probabilities for various bit strings. You see that they form, they show different Porter-Thomas distribution, but with which differ in the mean values. So the mean values can be computed from the mean value is essentially determined by the initial state. Okay, so these plots showed some randomly picked bit strings for which I had plotted the distributions. I can take, to exhaustively understand what happens, you can look at the distribution of the Kullback-Leibler divergence or the distance from the Porter-Thomas distribution for the different bit string. So for each bit string, I have a distribution like this, and I can compare that with the Porter-Thomas distribution that is expected from that bit string, and I can calculate the Kullback-Leibler divergence between the two. And since I have many, many bit strings, I can construct a distribution of divergences, distances from the PT distribution. And it turns out that if the measurement angle is pi by 2, alpha is the coefficient of pi in the measurement angle. If the measurement is done at pi by 2, then the distribution of Kullback-Leibler divergence is very close to 0. And as you make the temporal ensemble, the time scale over which you make the binning to be finer, you get something that is even closer to 0. And even if the measurement angle is closer to the polar angle, to the poles, if it is pi by 5, still the distribution is very close to 0. If you go to very small measurement angles, it turns out that the distribution starts deviating from the Porter-Thomas distribution. That is suggested by the fact that there are some rare bit strings for which the Kullback-Leibler divergence is very large. So this is at angle 0.125 or pi by 8. So as you go to measurement angles that are close to the poles, then the probabilities of probability distributions of the probabilities deviate from the Porter-Thomas distribution. Now, as an aside, instead of calculating the bit string probability distribution at a particular bit string, if I calculate the distribution of the probabilities for a given time, it turns out that at measurement angle 0.5, it is exactly the Porter-Thomas distribution. Every bit string has identical Porter-Thomas distribution. However, if you calculate the probability of getting various bit strings in the case where the measurement angle is different from pi by 2, it turns out that you get a distribution that is not Porter-Thomas, but you can argue that this is actually a linear combination of exponential distribution, linear combination of Porter-Thomas distribution, and this is what you get from constructing that linear combination, and the blue shows the actual numerically obtained distribution at a measurement angle pi by 4. Okay, now coming to the projected moments of the projected ensemble. For illustration, I'll consider the case where I have a single spin on A subsystem and a larger and a large B subsystem. At a generic time, if the initial angle of the initial state of the A site was cosine theta by 2 times 0 plus sine theta by 2 times 1, after a long time evolution with the L-bit Hamiltonian, the state can be written as an entangled state between A and B, and it will have this form. Alpha 0 is the alpha 0 and alpha 1 are states of B. If you make projective measurements on the B subsystem, then if the B subsystem produces some bit string ZB, when I say ZB, it doesn't necessarily have to be in the Z direction. This measurement could have been in some other angle. Z is just a generic label for the bit string. If you get some particular bit string ZB in the B subsystem, when you make a projective measurement, then the corresponding state that appears in A is of this form, where square root of where P is the probability that this particular the probability that ZB is the bit string that is measured, and P of ZB can be calculated to be this in a very straightforward way. Now, if you calculate the so I can calculate one of the matrix elements of the second moment just for illustration. It'll have this form. This is the coefficient of the 0A state to the power of 4, which comes from, that's the term that appears in the matrix element 0, 0, 0, 0 of the second moment. And the P squared in the denominator comes from the normalization, and P here comes from the weighted average of these quantities. This is the second moment, the matrix element of the second moment at one of the diagonal matrix elements of the second moment. If you calculate this, you can rewrite this using this form in this way. And this can be numerically computed. And if you numerically compute, you see that as time progresses, the numerical value approaches a constant value. And therefore, it's a time independent at large times. And if you assume that this quantity is time independent at large times, then I can average this over time. And if I average this quantity over time, I can replace the sum over ZB. I can do an ensemble average, the temporal ensemble average over Porter-Thomas distribution for these coefficients. And if you assume at large times that these coefficients are independent, then I can use the Porter-Thomas distribution and rewrite this with a little bit of algebra into this form. Now, you see that this is this form of the moments, the matrix elements of the moments are almost identical to what you had. Indeed, they are identical to what we had for the moments of the Scrooge ensemble, where if you recognize that the density matrix of the subsystem A at large time would be the diagonal ensemble cosine squared theta by 2 and sine squared theta by 2. So lambda n and the lambda I is appearing here are cosine squared theta by 2 and sine squared theta by 2. And then that means that these two are identical to each other. And therefore, it shows that if at large times the bit string probability distributions match the Porter-Thomas distribution, then we will be able to, we will find that the moments of the projected ensemble become identical to the moments of the Scrooge ensemble. We can numerically compute this and compare with the expected Scrooge ensemble values. This is the long time averaged moment. Those are these lines. Different lines indicate different sizes of the LB subsystem. the dotted line is the estimate from the Scrooge ensemble. And as you can see that, and the x-axis is the measurement angle divided by pi. So at pi by 2, if the measurements are done at in the x basis, then it turns out that the moments match the Scrooge ensemble. And for a large range of angles around pi by 2, the numerically obtained moments match the Scrooge ensemble. The moments deviate from the Scrooge ensemble only for angles very close to 0. And as you go to larger and larger systems, the moments match with the Scrooge, larger and larger B subsystems, the moments match the Scrooge ensemble better. And qualitatively, the behavior was the same for, this is shown for LA equal to 1, and this is for LA equal to 2, the subsystem A where the Scrooge ensemble is being constructed, or the projected ensemble is being constructed. And qualitative behavior is the same for LA equal to 1 and LA equal to 2. Now, the specific features of the Hamiltonian shows up in the initial time dependence only. So this is a plot of the time dependence of the deviation from the Scrooge ensemble for 2 different cases. The blue one shows the deviations for the case where the measurements were done at some angle, I think pi by 4 from the z-axis, and the green one shows the different deviation of the moments from the Scrooge ensemble for when the measurements were done in the x direction. In general, the 3 different lines show the deviations for LB system size, the total system size 20, 14, and 10. The moments approach the Scrooge ensemble, and ideally for the Scrooge ensemble, the difference will be 0. As time progresses, the moments keep approaching the Scrooge ensemble value. For a finite size system, the deviation shows a finite value, saturates at a finite value. The value at which it saturates decreases with LB, and the initial time, and generally we find that the moments approach the Scrooge ensemble as a power law in time, and the difference in Scrooge ensemble, as I mentioned, saturates to a non-zero value for a finite LB, and the time at which the saturation happens grows with LB. And the saturation value exponentially decays with LB, as you can see this linearly going down with increasing system size L in the log scale. The angle dependence, so if the approach to the Scrooge ensemble is faster if the measurement is done at closer to the x-axis, that is least charge revealing measurements, and the saturation values are closer to the Scrooge value again when the measurements are least charge revealing. The qualitative behavior is the same for second and third moments for LA equal to 1 and 2. So to conclude, based on the first 3 moment calculations, the projected ensemble approaches the Scrooge ensemble at large times for large LB, and this is true for all angle of measurement except for measurement angles close to the z-axis. There is an initial transient time when the system shows some angle dependence in the evolution. For angles closer to x-axis, the Scrooge ensemble is approached faster. So this is different from what is seen in the global case where there are global conserved charges. In those cases, the eventual ensemble that is approached depends on the measurement direction. And the approach to the Scrooge ensemble can be traced back to the bit string probabilities distribution and how well it approaches the Porter-Thomas distribution. Now, we had looked at the first 3 moments, whether the higher moments also agree with the Scrooge ensemble. That's hard to determine numerically. It is possible that the cross correlate, I had assumed that the certain coefficients are independent at large times. Whether this is true, strictly true, is not clear, and therefore cross correlations between bit strings, and also there may be fine deviations from the Porter-Thomas distributions when the measurement angle is different from the x basis, And these may show up at higher moments, but at least in the first 2-3 moments, it's not discernible, at least numerically. So that's the.
Questions, please.
You take one particular model and they are talk about this X measurement is particularly special. Why is that?
So X measurement, it has some special features. It is, okay, so it has.
You said that it is Z prepared, that's why X is something you made some statement.
It is possible that it is because there are local conserved charges which are the sigma z's.
Yeah.
X measurement is special in the sense that when you make an X measurement and you get a particular value, it tells you nothing about what was the Z conserved charge.
So that then same is true for Y also, no?
Oh yeah, it will be true for Y measurement also. So here we changed only in the axis, XZ axis.
Yes. So another comment just it is, so this, you cite one paper by Utters and Deutsch probably, no? Jossa.
Yeah.
This about this optimal accessible information from a quantum ensemble.
Right.
Actually, this is first work is done by Hollebow in 1973. This is called Hollebow bound.
Oh, that is the upper bound. That's the maximal accessible information. But this is the minimum accessible information.
Oh, they gives a lower bound.
Yeah, this gives a lower bound. So this is the.
But what is the meaning of lower bound? If I do a completely wrong measurement, then I will get zero, nothing.
The accessible information is the direction in which you get the maximum information.
Yes.
Correspond to the, among the maximum, this is the minimum. If you optimize the measurement directions such that you get the maximum information from the communication.
So among the maximum means you are talking about the supremum value.
Yeah.
That is
So the
Hollebow
particular
bound.
distribution from which the messages are taken, such in which the maximum that the B subsystem can access, the observer can get, is the minimum. That is the.
Okay, I'll go to their paper because I don't know their paper. We used to read this Hollebow's paper.
Yeah, this is the opposite limit.
I see.
Further questions? Probably, I have a very naive, silly question. So what is this screws ensemble special about? I mean, why did you introduce this ensemble?
Yeah, so it is prescribing a. So given a density matrix, you could have different ensembles from where that density matrix could have come. The ensemble that, in some intuitive sense, which is the most broadly distributed in the full Hilbert space, that ensemble is the Scrooge ensemble. So if you sort of intuitively think of a broad distribution in the Hilbert space itself. So this is the broadest distribution in the Hilbert space such that the density matrix is the given density matrix.
Oh, I see.
So in that sense, it is the maximum entropy distribution in the Hilbert space such that the density matrix is the same for a particular given.
And in your model, you have taken a long range model?
This is a short range. The coupling constants decrease exponentially with distance between the qubits.
I see. And the system, I mean, has some asymptotic limit reaches the screws ensemble. So in the intermediate angle, I mean, what kind of ensemble?
Intermediate time, you mean? Oh, intermediate other angles. Yeah, I do not know exactly what ensemble of. You're asking about this.
Yeah.
It's not clear exactly at Z measurement. It turns out it's sort of a trivial result. You will essentially get something that is uniquely determined. There will be no time evolution in the moments, but if you slightly go to the right of z-axis, which means theta is slightly greater than 0, in that case, I guess from the look of this plot, it seems that if you got a really large LP for any angle other than theta equal to 0, you will reach the Scrooge ensemble. Whether that's strictly true, I do not know, but given this, the form of this plot, that is what it looks like.
Thank you. If there is no other question, let's thank Sreejith for the nice talk.